Okay, so Lee gave a nice background to then lead into Ate going into more detail into some of these scientific pieces related to the groundwater age. And Ate Visser is a research scientist in the Environmental Radiochemistry group at Lawrence Livermore National Laboratory. His research centers around the applications of environmental tracers and hydrology to get a better understanding of the processes of groundwater flow, contaminant transport, and water resources sustainability. His expertise is in combining multiple environmental tracers to calculate residence time distributions of sampled water. His work involves developing the compatibility to measure new tracers at Lawrence Livermore National Laboratory and applying them to California's pressing water questions. Yet, the best part of his job is going out into the field to collect the samples, which he's been doing this week, so he must be very happy today. So thank you, Ate.
Very happy and a little bit tired because that was me. We were there a couple hours ago trying to get as much water, and that's why I was a little late. Because more water is better. You need to be closer. Yeah.
Try it.
So what can we? So this is what I want to talk about. What can we learn from tracers? What tracers do we have available? What underlying assumptions do we use interpreting the data of the tracers? What does 3D helium dating mean? And what has been done, and what are we doing this week and this for the Gamma 15 project that brings me up here. So we didn't coordinate what the questions are that we want to answer between Lee and me, but we came up with the same three questions. Where does the water come from? How does it get here? And how long does it take to get here? And related to the third one is how much water is stored along the way, because those two are intrinsically linked. For the sources, there are a number of tracers, like Lee showed, that can fingerprint where the water came from. There are a number of tracers that show how the water got here, because the water flows on the ground and picks up minerals and chemistry changes along the way, and mapping the chemistry is really helpful to show where it came from. And then how long does it take to get here? We need certain tracers that record when it recharged, or record how long it's been underway. So those are the travel time tracers. This is another list of the three. I already covered most of what I had on here. The stable isotopes are very useful for the fingerprinting of where the water came from. So the stable isotopes of water are either deuterium, which is a heavier atom of hydrogen. So water is a hydrogen atom, and normal water is hydrogen, oxygen, hydrogen. The heavy water is hydrogen, oxygen, deuterium. And there's a third isotope of hydrogen that is tritium, and it's a radioactive isotope. And because it's radioactive, it decays, and it's very useful for dating. So that would be hydrogen, oxygen, tritium. And those travel time tracers are either radioactive tracers that are useful because they decay, so their activity or concentration decreases over time because of the radioactive decay, or some man-made chemicals are very useful as age tracers. We put out a lot of CFCs in refrigerators and hairspray, and that got into the atmosphere, so the concentration increased in the atmosphere, and we can see it in the water that we sample. That is useful. And some tracers accumulate over time in the groundwater. But first, before we go into...
I think you need the mic closer.
Even closer. Okay. I know I hear it. Sorry. We need to make sure we have understand the assumptions we need to make. So first, we say that a tracer is conservative. The tracer and the water need to stay together. If the tracer and the water can be separated in some way, then it's not a very good tracer, because the water we sample doesn't contain a tracer we want to sample. Secondly, the initial source signature needs to be known very well. So like Lee showed, if you want to know where the water came from, you need to know what the source signature is on top of the mountain. What is the source signature in the valley? And if we know those source signatures, you can compare them, and then you can draw conclusions. For the age tracers, the source signature sometimes changes over time. So for example, for tritium, it was released during nuclear testing, so we have a source history, and we need to know the source history very well to understand, to interpret the data we get. The third assumption is there is no additional source of the tracer we're measuring. Here on top of volcano, that's a bit of a problem for some of the tracers we like to use, because volcanoes emit the same kind of isotopes that we're interested in. And the fourth one, we need to know the decay rates of the radioactive isotopes, which is really are the least of our concerns. There are a lot of nuclear scientists working very hard on getting very accurate decay rates. So we don't worry about the last one as much. We worry a lot about the first three assumptions. So we need to make sure that those assumptions are valid before we draw any conclusions. Our go-to tool for groundwater dating is tritium helium dating. We have a lab that can do it, and it's been a very helpful tool. And under the right conditions, tritium helium age dates can be as accurate as 1 year, but only if the right conditions exist. So we need to be able to sample it without atmospheric contamination. So we need to sample either a well that hasn't been in contact with the atmosphere before we take our sample, or a spring. And we've been trying to collect spring samples, and we haven't been very lucky this week. So we've tried to skip them and not get weird data that we don't really understand. The second one is that it needs to be less than 60 years old, because beyond 60 years, that's really our horizon, because in the 1960s, about 60 years ago, 1950s, 60s, there was a lot of nuclear testing, and that was for a long time the main source of our tritium supply. The nuclear test introduced large amounts of the radioactive isotope into the atmosphere, and that rained out. And once it rains out and becomes part of the groundwater system, well, it decays anywhere it is, but once it becomes part of the groundwater system, its daughter product is helium-3. And in the groundwater system, the helium-3 is contained. So both the tritium and the helium-3 are together, and we basically have the top and the bottom half of an hourglass. And if you know the top and the bottom half of an hourglass, you know the time. So only under these conditions, the tritium-helium dating works really well. That means that you can't have anything that adds either tritium to the top half of the hourglass, or have anything that adds helium-3 to the bottom half of the hourglass. And here's where we run into trouble. First of all, I'll show some figures of how we measure it. It's not really straightforward. We need to take the sample, extract all the gases out of it, then we let it sit for a while, like it's in the groundwater system. So the tritium decays and accumulates helium-3, and after a while we take that sample again, put it on a machine, and measure how much helium-3 was accumulated. So it's an indirect way of measuring it, but we can do it pretty accurately and to a very low level. Now here's where we run into trouble. Being in this beautiful surrounding with Mount Shasta on the background, we find that Mount Shasta is a conduit to the mantle of the Earth. So in the past, a lot of materials from the mantle of the Earth have come up. They brought with them a lot of helium, including helium-3. So that adds something to the bottom half of the hourglass. So in some cases, sampling thorium helium here doesn't really help us, because we only have the top half of the hourglass. Luckily, we can detect when that happens, because it also releases helium-4. So it's not that we're completely blind, but we know when the bottom half is broken. But when the bottom half is broken, we can only rely on the top half. So there have been, as far as I could find, 3 studies published, and there are a few more that haven't been out, I think, that have collected samples here in the area and have relied on tritium helium dating. And I summarized some of the results here. But I'll only look at the tritium, because I am not familiar enough with the details of every sample that I trust the helium-3 completely. So the tritium values we see in the literature are between 13.1 picocurie per liter and less than 0.4 for the bottom one, which is a mese well in weed. For reference, the maximum contaminant level for tritium is 20,000. So although it's a radioactive isotope, it's at a level that is way beyond any of the other harmful for humans or anything, and way lower than most analytical labs will be able to detect it. Going back to what this means for the ages of the water here. If it starts at 13.1 picocuries per liter, and if we assume that is the source fingerprint, then all the other waters we've said or that have been sampled are somewhat older. So their concentrations is lower than what they started with because of the radioactive decay between the time it recharged and the time we sampled it. And the only well that we can't date anymore because it's so low that we can't really quantify the concentration is the Mese well. So that it's probably entirely older than 1950. All the other ones have a component of water that is between 1950 and present. But it's really hard to determine exactly what that component is. Why is that so hard? Well, the stable isotopes vary across the US, but also the tritium input function varies across the US. Because of different atmospheric processes, tritium is typically higher at higher latitudes, so near Canada, and higher in higher elevation, because there is more mixing with the upper atmosphere. On top of that, the main source of tritium in the 60s introduced a lot of tritium in the atmosphere, but that has been raining out. So over time, the input function is changing, it's decreasing and decreasing. But to make it even worse, there is some seasonal effect that causes annual variation in tritium. So it's really hard to get the right source signature for tritium. For the past 2 years, we had a student, Patrick Harms, who tried to get a better grip of that source signature. I can go back one, yes. So the curves I'm showing here is, one is from Ottawa in Canada. We always use that one because it's the longest and most continuous record we have. The other in red is from Menlo Park, where the USGS has been sampling precipitation for a while. They've done a really good job and it's really useful, but at some point, I think in the 80s or 90s, this found that a local source emitted tritium to the atmosphere, so they stopped their station. Since then, we haven't had any local stations in California. What you also see is that there are little gaps in there. These gaps are basically, when there is no rain, there is no sample. So it gets harder to make a nice continuous time series. To get a better grip of the input again, the student went all across the state and sampled surface waters. Surface waters are not the ideal sample to take if you're looking at a precipitation signal, but they're the best thing if you don't want to set up precipitation stations everywhere, which is really expensive. And even based on the surface water, we could draw some conclusions that there is an inland trend, like we showed on the map before, that the coastal regions have lower concentrations of tritium, and the inland, mainly in the southern Shiras, show very high here, very high or higher concentrations, up to 15 to 20 picocuries. But there is also a seasonal trend, as we saw on the graphs. So we're having trouble and we're trying to get a better grip on the source signature, because if we know the source signature better, we can say more found and make much better conclusions about the age of water. So we like to use one curve for the state, but we've got to keep in the back of our minds that there is this, between the Bay Area, it's about 6 to 8 picocuries, and this Martis Valley, where we sampled, in Sierra Nevada, it's between 8 and 20. So it's not as accurate as we would like to know. What we can assume here as a first shot at it is that the highest value we measured is the youngest. It represents present-day precipitation. So that was McLeod Upper Spring at 13.1 picocuries. Using that, we basically erased the entire curve to make that fit. And then all the other samples we have, we can correct for the decay and see where they would have maybe possibly recharged. So for a number of them, they're likely 10 to 20 years old. Another group of them are possibly 20 to 35 years old, but they're sort of touching a curve, and there might be some mixture with pre-modern, with groundwater, which is older than 60 years. And some of them, like Carrick Springs and Bowen Springs, they don't make sense in a way that there must be some really old water being mixed in, because otherwise you don't get those sample values today. So we're getting a slightly better grip on the residence times and ages here in this system. But to get even a better grip, we want to add more tracers, have more tools, and base our conclusions on multiple lines of evidence. So we're sampling for 4 different age tracers, including tritium, that all have different half-lives. So it ranges from an isotope of sulfur, which has a 87-day half-life, to sodium isotope, which has a 2.6-year half-life, to tritium, which has a 12.3-year half-life, and we also include krypton-95. And I'll show you how that works later. I gotta say, we haven't been doing this for a long time yet. We have been doing sulfur-35 for a few years, and we're getting sort of a feel for what the input function is and how it behaves. We haven't done sodium, really, we haven't measured it. We're collecting samples, and we hope to set up the capability soon. So this is experimental research. So I'm trying to play down your expectations that we're doing our best, but we can't promise to get you a very accurate age, because it may or may not work. That's sort of the nature of my game. The design of our study here is collect samples from different elevations, from different distances to Mount Shasta, and from different aspects to Mount Shasta. And it's sort of a cross-section in Mount Shasta City. So the 3 curves there show how the 3 age traces ideally behave and would decay. If you measure a lot of them, of all 3 of them, the water must be very young. If we measure no sulfur-35, so no blue line, and still a lot of the other ones, it must be around 1 year old. If we measure a lot of the tritium and krypton-95, but none of the sodium and sulfur-35, it must be somewhat older. And then if we measure only tritium, but no krypton-85, it must be that range that the krypton is gone, but the green tritium is still there. So that's our approach of trying to figure out how old water is. Tritium has a natural source as well, beside nuclear testing. Sulfur-35 and sodium-22 might have been produced during testing, I'm not sure. But they're sources in the upper atmosphere. When particles from outer space hit argon atoms in the upper atmosphere, they literally break down the argon atoms and they split into pieces, and those pieces are sometimes sodium-22, sometimes sulfur-35, sometimes something else. Sodium-22 and sulfur-35 rain out with the tritium, and then we try to measure them at the lab. To get an idea of how rare they are, there is roughly 1 tritium atom in natural rain for every 1 with 18 zeros of hydrogen atoms. It's roughly the same ratio as putting a red grain of rice in a truck full of rice. And then taking trucks of rice and put them all around the equator. Wow. And that's the ratio. So some of it is a bit hard. The reason why we can detect it is because they're radioactive, so they emit something when they actually decay. In case of helium or tritium, it decays to something else we can measure. So if it was just a red grain of rice in a truck full of rice, we have no chance. Because they're so rare, we need a lot of water. For sulfur-35, we need about 5 gallons. Sometimes we can do with less. Ideally, we have more, because more sample means more signal and better accuracies. So for sulfur-35, we collect the carboys. In the lab, we let the sulfur absorb to a resin, and then get it off the resin again to concentrate it in a smaller volume of water, and then we can precipitate it, make it react, and it becomes salt, and we can concentrate it even further and then put it on what they call a liquid simulation counter, where the decays of the sulfur are actually counted. They create a little bit of light. Sodium-22 is even a bigger nightmare because we need 100 gallons, and we can collect 100 gallons for every sample we take. So here, the resin we take out in the field, we rinse the 100 gallons through it, take the resin back to the lab. The resin looks like this. It's not a big setup, it's about big. And we do the same old trick. We rinse it with acid, the sodium comes off again, so we can concentrate it and we can count it. The last one I haven't talked about is the Krypton 85. It's a little bit more established. There are a number of labs that can do this. It's produced by nuclear reactions in the core of a nuclear power plant. Usually, as long as you don't do anything to the fuel rods, the Krypton 95 is trapped. If you reprocess the fuel, it gets released to the atmosphere. So there are only a few locations on Earth that they reprocess fuel, which makes it a good tracer because you don't have anybody with a nuclear fuel reprocessing plant in their backyard. So we know the atmosphere is very well mixed and the input function is very well known. That's the good part of it. The bad part is we need even more water. We need 1,000 gallons. So this time we have a contraption that runs the water through, extracts the gas, including krypton, and compresses it in one of those red tanks. And then in the lab we have a setup that we can extract the krypton out of it, and then take a little bit of the krypton, which adds to, I think it's about a grain of rice, and then we can count what decays in there. So these tracers are, you might get a feel for why not everybody has been using them yet. It's just a lot of work. This is our setup of our study here. We've been sampling wells in Weed and Trout in Mount Shasta, so they get different aspects of the Mount Shasta volcano. And we're sampling a number of wells across Mount Shasta. I must confess that was my traditional hydrogeologist that thought water comes from a mountain and flows from one end to the other end of town, and that's where it discharges. We might find that water doesn't age from high up on a mountain to down in the valley. We will see. So this is the cross-section of wells we're sampling across Mount Shasta. Some of them are domestic wells, some of them are the big production wells that the city owns. We're trying to sample a gold spring tomorrow as well, and we hope to get a full suite of tracers, but as I said, we have some trouble with collecting good spring samples. Finally, what do we expect to find? Well, we expect to get better constraint on the age distribution of water. I'm very careful. I'm not going to promise you I will tell you how old your water is, because we might not get there. We hope to get a better, narrow it down to this much water might be younger than 1 year, this might be younger than 50 years, this much is around 10 years, maybe, if we're lucky. Maybe we find evidence of fast flow paths. If we find the decaying tracers that decay really fast, if we detect them, we know they've been recharged very recently. Maybe we'll find them, maybe we'll see blanks and everything is older, we don't know yet. Ultimately, we hope to provide an estimate of the volume of water stored along the flow paths, feeding the springs and wells that are discharging in this area. We can only estimate the flow path combined with measurements of flow, so we really need those measurements of flow as well to get to answer that question. And ultimately, we want to get a better understanding of the water flow on, in, and around Mount Shasta. And I hope we succeed in part of our work. Thanks for your attention. I appreciate it. I need to acknowledge our sponsors. It sounds very bad, but we're very grateful for, we've been working with the State of California Water Boards. It was one of the harder abbreviations earlier in the evening. They're funding a number of studies for us, we're called the special studies, where we try to develop new tracers. They've also been funding the Gamma Periodic Basin project, for which I showed some results. So those projects are very useful because they give a baseline and also try to develop new ways of looking at hydrological systems in California and getting more groundwater science to actually work. And finally, now I still have the time and opportunity, I want to thank everybody who's been participating here. We've been meeting a lot of very helpful people, and it's been great working here this week. So with that, I'd like to thank you again.
Okay, thank you so much, Mary and Lee and Atta. I think that we now have a nice round, at least 15 minutes for questions, and I'd just like to take the mic, just invite the three of you to come up in the front, and I can, if there's slides that people have questions about, so I can get them back and then just pass the mic between you. So I know that you had a question right at the beginning for Mary. Would you like to remember that?
You were talking about the state says that the water should be taken care of at the local level first, and then that they'll intervene if the local agencies don't do their due diligence. In Siskiyou County, our Board of Supervisors and our City Council have not done their due diligence in a current situation regarding water. So when no local agency will step up and be the lead agency in taking care of our natural resource, where do we go from there?
If they don't form the local groundwater sustainability agency by June 30th, 2017, then the State Water Board can come in and act as that groundwater sustainability agency until the locals are ready to take it over.
When you say locals, do you mean locals, government agencies?
There has to be a local public agency. So it could be a water district, but they only have authority over the area of their, the outline of their boundaries. It could be a county, it could be a combination of them. But pretty much the general feel that we've had, nobody wants the state board to come in and take over. So I think there's going to be a real effort by locals to step up, because you guys know your water conditions so much better than somebody from Sacramento.
We know them better than our politicians.
I can't comment on that.
Thank you. Are there more questions?
This is to Ate and Lee. You talked about the age of the water, the rate that it flows from the source, where is the source location. One important question here is how robust is the source? For example, during a drought, how much does the water level drop? Or even in non-drought times, if water is withdrawn by, say, heavy industrial pumping, like we're facing here, how much will the groundwater level go down? Do your results or approaches bear on that problem of the robustness?
I tried to emphasize in my talk that there's evidence to suggest that the response to the spring levels are immediate to changes in the input, in particular the precipitation input. At least that's from the case from the Fall River Spring system, as well as over the course of the 87-92 drought for the Hat Creek system. I haven't seen data in the Mount Shasta region to that extent. I think that's one of the goals that I would advocate to start monitoring springs closely and couple those to the precipitation input. How that's related to age of the water, I don't know that I ought to handle that.
Thanks. how it relates to age is that if you know your volume going out every year, and you know how long it's been in there, you can make an estimate of how much water is still on its way that will come out under current conditions. If you know the volume that's currently in the system, it gives some indications of how vulnerable it is. If it's just a 1 year lead time, then you're in bigger trouble if there's a drought and if there is 50 years of water waiting to discharge.